in this video we will discuss 73 symmorphic space groups. Remember, when we were discussing the introduction to space groups, we classified space groups into one of the classifications, one of the possible classification of three-dimensional space groups is in 73 symmorphic space groups and the remaining non-symmorphic space groups. We had defined symmorphic space groups in an earlier video, but we will redefine it here and look at how do we get these 73 symmorphic space groups. So, the definition of symmorphic space group is a space group which are generated only by symmorphic operations. So, recall that symmorphic operations are lattice translations, rotations and roto-inversions. So, what is left out in this? It may look like that we are considering all operations, translations, rotations and roto-inversions, but no, we are leaving out two important kinds of operations, which are screw and glide. They are non-symmorphic operations. So, if we leave out those non-symmorphic operations and generate a space group only by symmorphic operations, that is only by lattice translations, rotations and roto-inversions, and as you know, roto-inversions include inversions and reflections. Now, if you look at the lattice translations, so these actually determine 14 Bravais lattices. So, the different kind of lattice translations which a lattice can have, which a periodic pattern can have, is classified into 14 Bravais lattices. And we have also seen in detail that different kinds of rotations and roto-inversions form point groups, and they can be classified into 32 point groups. So, essentially that means that if we want to combine these to form our space groups, we have 14 Bravais lattices and 32 point groups to play with. So, it may appear that we can simply multiply these two numbers, that 14 different kinds of lattices are there and we can combine them with 32 different kinds of point groups. So, we should be able to generate 484 space groups. Only this is not right. This is not right, and as we know that there are only 230 three-dimensional space groups. So, what happens here? Why we do not get this a number 484 and instead only a limited number of 230 space groups? So, this is because of an important requirement that a point group can be combined with a Bravais lattice only in a symmetry consistent way to generate a space group. Let me show you what does this mean. So, although we are now intending to discuss three-dimensional space group, but still it is simpler for me to show this in a 2D example, which we have discussed in our plane group discussion in other videos. But let me try to show you one simple case. So, let me draw a square unit cell. So, this is a square unit cell representing a square lattice in 2 dimension. Suppose I put an object with threefold symmetry at the corners. So, the presence of these threefold symmetry triangles, assume them to be equilateral triangles. I have not been able to draw it very nicely. So, because of their presence, the fourfold of the entire pattern is disturbed and is gone. So, although I repeat these triangles in a square lattice, I will not get a pattern with a fourfold symmetry. So, I will not call that a square space group belonging to, or plane group belonging to a square lattice. So, the squareness can be preserved only if we put objects which are consistent with the square symmetry. So, this space group, for example, this plane group, if my triangles are oriented this way, will preserve the mirror planes, but not the four folds. And since the mirror planes are preserved and only one set of mirror planes are there, you know that we call this plane group as P M, and it is not, let us say, it will not be P 4 or P 4 mm. So, we do not generate new plane groups by putting an object with a different point group than what is consistent with that particular 2-dimensional lattice. So, this also is true for the 3-dimensional case. So, we will always have to put objects which are consistent with the corresponding symmetry which the lattice represents to generate new space groups. So, let us do that now one by one. So, for 3-dimensional case, the symmetry of the lattice is classified into crystal systems. So, for example, in the triclinic crystal system, we have only one Bravais lattice, which is the primitive triclinic. The triclinic symbol is A, representing anorthic, and we have seen that in the triclinic system there are only two point group symmetries possible, 1 and 1 bar, identity or center of inversion. So, only these two point groups are there and only one lattice is there. So, we can put these point groups to associate the objects with these point groups to the triclinic lattice, the primitive triclinic lattice, and that will generate two space groups for me whose Hermann-Mauguin symbols are P 1 and P 1 bar. So, these are actually the first two space groups in the international table. Space group number 1 is P 1 and space group number 2 is P 1 bar. Now, as we go down in this list, so suppose we consider the monoclinic crystal system, the required symmetry is a single two-fold, but it gives me two Bravais lattices, monoclinic P, primitive monoclinic, and monoclinic C, the end centered or base centered monoclinic. So, this will then give me, and there are 3 point groups 2 m and 2 by m. So, if I combine these point groups with MP, I get the first row of space group P 2, P by m and P 2 by m, and if I combine the end centered monoclinic with these 3 point groups, I get another 3 space group in the second row C 2, C m and C 2 by m. So, we continue this process with other crystal system. So, here is orthorhombic. So, you can see in orthorhombic we know that there are 4 lattices: primitive, body centered, face centered and end centered. S represents a general end centered, which can be either A, B or C. So, if we combine this 4 lattices, and in the orthorhombic system there are 3 point groups. So, 3 into 4, 12 space groups you generate here. So, the primitive lattice with these 3 point groups will give P 2 2, P m m 2 and P m m m, and so on. Tetragonal has now 7 point groups. The required symmetry is a single 4-fold or 4 bar, that, as we have seen in the analysis of 32 point groups, gives us 7 tetragonal point groups, and there are 2 tetragonal Bravais lattices T p and T I. So, if I combine the 7 point groups with these 2 lattices, I get 14 space groups which are represented here. So, for example, if I put 4 on a body centered tetragonal lattice, I will get I will get I 4 Have I missed writing it? Yeah, I am writing a less number of for P I have written all 7. For I think I made a mistake here. Let me correct that for you and for myself also. These should not be repeated with P, these should be repeated with I. I just got that mistake, so let me fix this. So I 4 I 4 bar 2 and I 4 by So, as I was telling that if I put 4 point group on a TI lattice, tetragonal body centered lattice, then I will get I 4 space group. So, similarly for others. Trigonal has two lattices, hexagonal P and hexagonal R. I have another video which discusses this in detail, and there are 5 point groups 3 bar, 3 3 2 and 3 bar m. So, each of them combined with these two lattices give you the 10 point groups shown here. Hexagonal has again 7 point groups, but there is only one lattice associated with hexagon, the hexagonal primitive. So, that generates the 7 point groups shown here. And cubic, you have 3 Bravais lattices, primitive cubic, body centered cubic and face centered cubic, and you have 5 point groups. You can generate 15 consistent Bravais lattices. So, 15 consistent space groups. So, let us count the number, how many we have got. So, this is 2 into 1. So, we have 2 here, we have 6 in the monoclinic, 4 into 3, 12 in the orthorhombic, 7 into 2, so 14 in tetragonal, 5 into 2, 10 trigonal, and 6 into 1, so 6 hexagonal, and 5 into 3, 15 cubic groups. So, if you add all these numbers 2 plus 6 plus 12 plus 14 plus 10 plus 6 and 15, you get the number of space groups, number of symmorphic space groups which we have generated is 66. However, as we noted in the title to this video, there are 73 space groups. So, 7 of them are still missing. So, where are the missing 7? Because it seems we have already combined the point groups with the lattices in a consistent way. So, we should have got all of them, but we have not got, 7 of them are missing. So, let us look for the missing ones. Now, when you come to an orthorhombic lattice, this particular point group is interesting, MM2, and this particular lattice, that OS, is also interesting. Why they are interesting? Let us see. So, for example, in an orthorhombic lattice, when you have, so this is my, let us say, orthorhombic unit cell, and I am putting an object with MM2 symmetry. Now, MM2 symmetry itself means that I have an M and I have another orthogonal M. So, there are two perpendicular mirror planes and the intersection of them is a two-fold axis. So, that is what is meant by an MM2 point group. So, it has a unique two-fold axis, and if I look at the orthorhombic end-centered orthorhombic, and we have taken here, for example, I told you that it can be either A, B or C, and here we have taken C as the example in the generation of a space group. So, C means if this is my C axis, so C face is centered. So, the lattice points are shown by these red dots. So, that means one face is centered and one pair of face is centered, the other two pairs of faces, the vertical faces, are not centered. Now, I can put my MM2 point group in two possible orientations. Either the two-fold of MM2 can be like this, in which case the mirrors are going this way. So, mirrors are parallel to the uncentered face of the unit cell. However, if I tilt this and make the two-fold pass this way, let me try to draw it in a different color. So, if I take the green orientation of the two-fold, then the mirror planes, the two-fold axis now is passing through an uncentered face. So, because there is centered face and uncentered face, there are two possible orientation for the MM2 object with MM2 point group, which can be placed in this lattice with its two-fold perpendicular to the centered face or two-fold perpendicular to uncentered face. If you place it the two-fold in the uncentered face, then you generate a new space group, and that will be called, now since we prefer to call the centered, we prefer to call the two-fold direction as our C direction. So, in the green case, this will be my C face. So, the centering is now no more on the C face. So, this will be called in that case an A face. So, the centering is now A centered, A MM2. So, we generate a new point group because of this different orientation A MM2, and we create one new space group. So, this is one of the 7 missing ones. In tetragonal, similar situation comes with the point group 4 bar M2. So, in tetragonal, let me draw the square face of the tetragonal, and in the 4 bar M2 plane group, sorry, in the 4 bar M2 point group, there are mirror planes. There is a 4 bar in the center. If you recall the development of 4 bar M2, which is discussed in detail in another of my video, then you will find that it has two perpendicular mirrors as well as two perpendicular two-folds. Now, this can be placed exactly in this orientation, such that the mirror planes are parallel to the cube edge. Sorry, the mirror planes are perpendicular to the edges of the unit cell, the square edges of the unit cell, and the two folds are along the diagonal. Two folds are along the diagonal. But you can of course imagine another orientation possible. I have run out of space, so let me clear this and create another little square. And in this case, I will now put the two fold along the square edges, parallel to the square edges, whereas mirrors in the perpendicular direction. So you can see this is actually the same point group, but oriented differently with respect to the lattice. And because of this difference in orientation, the symmetry, because the space group captures not just the individual symmetry elements, but their interrelations also. So, the way the mirror planes and two-fold axes are related to the translational symmetry are different in these two cases. So, you will generate different point groups if you place it in this different way. So, one of them will be called 4 bar M2. See, I have already mixing up the notation. So, I have written here 4 bar M2, but here I wrote 4 bar 2M. So, maybe I should have written, originally I should have written. So, let me try to fix that. I was not being very careful, so that is a good learning for you also, that in this point group one has to be careful. So, in both cases, let me write whatever I had written initially, 4 bar M2 and 4 bar M2, but now for both the lattices, the primitive and the body centered, I generate two more space groups by putting it in a different orientation, and that is described by writing M and 2 in a different sequence. So, I have P 4 bar 2M and I 4 bar 2M. So, two new space groups get created in the tetragonal. In the trigonal, in the plane group also we had seen that actually the 3M has a single mirror, 3-2 has a single mirror, and 3 bar M has a single mirror, whereas the lattice has a rhombus base which has a short diagonal. Let me say a short diagonal, the black diagonal, or the long diagonal, which is a gold diagonal. These two directions are not symmetry equivalent. So, the question is whether I am placing the mirror in 3M and 3 bar M or the two fold in 3-2 along the short diagonal or the long diagonal. Depending on that, you will get two different kinds of space groups. So, really here this is not a complete description of the space group. This is not how in international table they will be given, but they will like to specify clearly that along which direction the mirror or two fold is aligned. So, in one case it will be written as P31M, P312 and P3 bar 1M, and in the other case it will be written as P3M1. So, M and 1 and 1 and M. So, they are changing place, and by their changing of place different space groups is getting created, P321 and P3 bar M1. So, you can see that 3 different space groups, new space groups are generated based on whether the mirror or two-fold in these 3 point groups are aligned along the short diagonal or long diagonal of the unit cell. So, this issue does not come with the rhombohedral case, because it has there the mirrors and the two folds can be placed only in a unique way. This freedom is not there to place them either along one direction or the other direction. So, you get here 3 new space groups. Now, we have gone into a lot of details. In the hexagonal, the same issue comes with 6 bar M2, because there is a mirror and there is a two-fold, and they can be aligned either along the short diagonal or along the long diagonal. So, here also you generate one more space group, which we will now call P 6 bar 2M. So, it is 6 bar M2, other orientation will be 6 bar 2M. So, with all this hard work, we have now probably found all the missing ones. 1 plus 2 3 plus 3 6 and 1 7. So, 66 plus 7 is equal to 73 symmorphic space groups we have found and listed here in their symbols. Of course, we are only giving the Hermann-Mauguin symbol of these space groups. We have not, and we have looked at little bit of their symmetries. The entire detailed symmetry one has to look up in the international tables, and we do not have time to look in the entire details, but what I have tried to explain you, that how does this number 73 for symmorphic space groups arise. Thank you very much.